Let's look at the product rule for derivatives. And before we dive into the derivatives to the product rule, let's talk about trig derivatives really quickly. I'm not going to give a full lesson on these. Really, it's best just to memorize these. There are ways to derive them yourself. However, if you saw the proofs of these derivatives, you would then say, you know what, I'm just going to memorize these because the proof is too difficult. So look at these, write those down, memorize them. A few trends that may help you memorize them, and I'm going to go through this quickly, is if you look at your co-functions. So when you look at sine and cosine, and when you look at tangent and cotangent, and when you look at secant and cosecant, you'll notice that all of the co-trigs, cosine, cotan, cosecant, they're all negative. Negative sine x. Derivative of cotan is negative cosecant squared. The derivative of cosecant is negative cosecant cotan. So notice that the derivatives of all the co-functions, all the co-trigs, are negative. And if you can remember sine, tangent, and secant, you'll notice that their co-functions, the derivatives, are the co-functions of the original. So sine's derivative is cosine. Cosine's derivative is sine, except it's negative. If you look at tangent and cotangent, their derivatives are secant squared and negative cosecant squared. And same thing with secant and cosecant. Secant's derivative is secant tangent. Cosecant's derivative is negative cosecant cotan. So a couple of trends that might help you keep them straight. That said, just memorize them. You're going to be using those all year, literally. Like, you won't stop until after the final exam or the AP exam. So let's move on to the product rule. You are supposed to use the product rule if you have a function that's in the form f of x times g of x. And those are two functions that could stand alone by themselves. One is not inside the other. They're written separately, and it is a product of two functions of x. And these are some examples of functions where you would use the product rule. So right here, number one, e to the x times x squared plus 4. You could consider f to be the function e to the x, and g is the function x squared plus 4, and you are multiplying the two, hence the name product rule. For number two, you have one function, x cubed, times a separate function, sine x. And then for this third example, you have sine x times ln x. So f is sine x, and g is the natural log of x. And both of those are functions of x. They have x's in them. You do not use the product rule if you have something like 4 times cosine x, because 4 does not have an x in it. While that is a product, it's 4 times cosine. Do not use the product rule for a constant times a function. Make sure they both have x's in them. And so the product rule itself, I'll leave this up here for a minute for you to look at it and write it down. If you are multiplying two functions and you want the derivative of f of x times g of x, then for the product rule, you do the derivative of f first, leave g alone, plus leave f alone, times the derivative of g. You just do the derivative of one at a time, and you add the two pieces. Now, the good thing about the product rule is it is the result of, the product rule has multiplication and addition, and both of those are commutative properties. So you can flip this around. It's kind of forgiving. A lot of people like to do the f g prime first, and then add the f prime g. And you could flip this around however you want, because multiplication and addition are forgiving. So you can flip that around how you want. Tired of saying that. Sometimes you will see derivative shortcuts written in terms of u and v. I don't know why the powers that be chose u and v a long time ago, but if you wanted to simplify it, you could say u, if y is u times v, then y prime is u prime v plus uv prime. And it's understood that u and v are functions of x. And so in that case, u and v would be functions of x, thus necessitating the product rule. And then finally, before we get into examples of the product rule, you want to always be on the lookout for ways that you can simplify your original function to avoid more difficult approaches. So these two problems right here, you can use the product rule, because I have x squared plus 2 times x minus 3. That is the product of two functions of x. However, if you channel your algebra skills at the very beginning, you could expand that, make that x cubed minus 3x squared plus 2x minus 6. And now I've reduced it from a product rule to a power rule. I've simplified the derivative approach. And number two is going to be even easier to clean up. You can easily distribute that x to the fifth and rewrite the function x to the 6th minus 5x to the 5th. And once again, we have reduced the problem to a power rule versus a product rule. So just because you see a product, always stop and think for a second. Can you clean it up into something simpler to make the calculus nicer for you? So let's do a few examples, and we're going to find the first derivatives of these first three problems. So if we have y equals e to the x times all this stuff, I'm looking at that. E to the x is my first function. I cannot clean that up. If I have two different types of functions, then I'm going to be forced into the product rule. So my first derivative, dy dx. I like to do the first function first. So the derivative of e to the x is e to the x. And then I will leave the x squared plus 5x minus 1 alone. So x squared plus 5x minus 1, I'm leaving that alone. Then we will add to that. Now I'm going to leave the first function alone, e to the x. And now we differentiate the second function. The derivative of x squared plus 5x is 2x plus 5. And there is your answer. If you need to, until you get comfortable with these, you might want to label your functions f and g. And then you can make note that this is f prime. The derivative of e to the x is e to the x. Here, I left the f function alone. Here, I left g alone. And on the second piece, I did the derivative of the g function. So if it helps you to label your functions f and g to organize your derivative process, you do that. But I do want you to eventually get to a point where you don't have to do that, because that is a time user. I wouldn't say it's wasting time, but it definitely uses more time. Okay, 2, we have another product. And here I did give you two polynomials. Those are the same type of function. So we have the option. If you want, we could fully expand this, but I have a trinomial times a quadrinomial, not a word you use very often. And in my opinion, the algebra to clean this up would be more difficult than the product rule. So while I have the option of expanding this, I'm not going to. I'm going to go straight into the product rule. So here's my function f, here's my function g, and we're going to product rule that. So my derivative, y prime, I'm going to start with the derivative of f, 3x squared plus 3, leave the g function alone, x to the 4th minus 5x squared plus x minus 17. Then I will add to that, and now we flip whichever one we did the derivative of. So I've already differentiated f, so this time I will leave it alone, x cubed plus 3x plus 1, and the derivative of the g function is going to be x to the 4th minus 5x squared plus x. No, it's not. I just copied it. This is supposed to be the derivative of g. So the derivative is going to be 4x cubed. Let's get this right. Minus 10x plus 1. And there is our product rule. And I am not going to clean these up anymore beyond the first derivative. There may be times later on in the year where we need to do some algebra to the end result, but right now I'm focusing on just getting through the product rule and making sure we understand the calculus behind the product rule. Okay, so let's look at 3, and 3 introduces a new situation where we now have a product of 3 functions. I have an e to the x, a sine x, and an x squared plus 3. So one of the approaches to this, and this is probably how a textbook would teach you to do it, is to group 2 of those together, and let's call that grouping the function f, and then we'll leave the second one or the last one alone, and we'll call that g. And now I'm going to do the product rule with this f, e to the x sine x, and the g, x squared plus 3. The problem is that the function f, e to the x times sine x, that is by itself a product rule. So I've got a product inside a product, and this is where derivatives get tricky, is when they layer the derivative approaches. So for f, that's a product. So now I'm going to product rule e to the x sine x. I'm going to start by leaving e to the x alone. Nope, I take that back. I'm going to do the derivative of e to the x. So the derivative of e to the x is e to the x. I'm going to leave sine x alone. Plus, now I'm going to leave e to the x alone, and I'll do the derivative of sine x, which is cosine x. And so right there, the derivative of f prime is a product. So I had a product inside a product. So that was all f prime. Now I'm going to leave g alone, x squared plus 3. Now I'm going to leave f alone, so e to the x sine x, I'm leaving alone. And now I will do the derivative of g, which is 2x. And so that is one approach to differentiating a product of three different functions. And I'm about to do the same problem a second time using a slightly different approach. And so looking at this function, what you can actually do is you can kind of expand your product rule approach to include three functions instead of just two. So my original product rule is if y is f times g, then the derivative is f prime g plus f g prime, where you just do the derivative of one piece, leave the other alone, and then you flip it around and add the two pieces together. I'm going to expand that trend, except this time I'm going to have an f, a g, and an h. And what you can actually do is you can find the derivative of just one piece at a time, leaving the other two alone. And as you march your way through the function, you just add all of the different products together. So I'm going to start with the derivative of f, and the derivative of f is e to the x. So I'll do the derivative of e to the x. That is e to the x. Now I'm going to leave the g and the h alone. So sine x, x squared plus 3. So I just did f prime. Now I'm going to move on. This time I'm going to do the derivative of g. So I'm going to leave e to the x alone. The derivative of g, derivative of sine, is cosine. So there I did g prime, and I'm leaving all of the other ones alone. So I'm going to leave x squared plus 3 alone. Plus, now I need to do the derivative of h. So I'm going to leave the e and the g functions alone. And it's time for the derivative of h, which would just be a 2x. So there's my h prime, and that is the same function, that is the same derivative that I got here. And if we did a little bit of algebra to my first approach, you will see that I have the same thing. And you can actually extend this pattern through as many different function products as exist, as you see. So if you had like 5 functions, then you could just do the derivative of one at a time, and you'll have 5 pieces being added together. But I won't do that to you. It's very rare. Actually, it's rare to even see a 3-headed product rule. But that is the approach you can use when you see more than just 2 things being multiplied. So there was the first derivative using the product rule. Let's talk about the second derivative. And when you get into second derivatives, you very frequently get into some ugly stuff, and you have to be very careful with your work. Now, I will preface number 4. If I were doing number 4 on my own and I weren't trying to make a point as a teacher, I would expand this. This is 2 binomials. They're easy to expand, and this would be easier if you did the algebra ahead of time to expand it and then did the derivative of the resulting polynomial. However, for the sake of practice with the product rule, I'm going to leave it as is, and I'm going to start with my first derivative. So my derivative of my first term would be 2x plus 5. Then I'll leave the second term alone, 4x cubed plus 7. Then I'm going to leave my first function alone, x squared plus 5. Now the derivative of my second function, 12x squared. So there is my first derivative, just a straightforward product rule of 2 polynomials. For my second derivative, what I've created is I've created 2 product rules. I have the sum of that product and this product. And so when I do my second derivative, I now have 2 product rules to consider. So my second derivative is going to be, and I'll do the product rule of this first piece. So that will be the derivative of 2x plus 5 is 2 times 4x cubed plus 7 plus, now I'm going to leave my first term alone, 2x plus 5, and the derivative is 12x squared plus, and now I'm going to do the product rule of my second term. So the derivative of x squared plus 5, 2x, leave the second one alone, plus leave the first alone, and the derivative of my second. And so there is one example of the second derivative of a product rule, and it does very frequently lead to multiple product rules, and it's quite ugly. It's so ugly that I just want to quit, although I could fairly easily distribute and combine some like terms, but I don't care. And the last example, finally, this one, and I think this is the last one. Yes, it is. All right, so here I have no algebra options to simplify this. It's an exponential function with a polynomial. You cannot avoid the product rule on this one. So I'm going to do my first derivative, y prime, is just going to be a normal product rule. So leave e to the x alone. I'm sorry, the derivative of e to the x is e to the x. I'm going to leave 2x cubed plus x alone. Now I'm leaving e to the x alone times the derivative of 2x cubed plus x. And so there's my first derivative. And before I dive straight into the second derivative, which a lot of people will, I always pause and think, is there something I can do to make my next derivative easier? And in this case, I absolutely can, because what I've got here is I have two things being added. I have this product and I have this product. And in each of those products, we have an e to the x. I can factor an e to the x out of this. So I'm going to take that e to the x out, take that e to the x out, and I'm going to rewrite my first derivative as e to the x times, I have 2x cubed plus x. I took that e to the x out, plus 6x squared plus 1. And when I factored that e to the x out, I turned my first derivative, I changed it from two products, this product plus that product. Now I have a single product, and my second derivative just got a lot quicker because I only have one product rule to think about. So now I'm going to do the derivative of e to the x. I'm going to leave this polynomial alone, 2x cubed plus 6x squared plus 1, plus now I'm leaving e to the x alone, and I will differentiate the polynomial 6x squared plus 1 plus 12x. And there is your second derivative of this function. And the main thing you want to remember, not the main thing, but one of the things you want to remember is always be on the lookout for ways that algebra can make your calculus easier. That should always be at least a fleeting thought before you dive straight into your calculus.